Hi everyone, Dr. Burns here with your second lesson of Chapter 4. We're going to talk about in this lesson the periodic trends in the properties of elements on our periodic table, as well as how to write electron configurations of ions and how the ionic radius varies on the periodic table. Now this first section that we're going to talk about is mainly definitions. And since we're talking about trends in our periodic table, you may find it useful to grab a fresh copy of your own periodic table to write those trends on it. So use a periodic table to write your trends. Because it really just comes down to knowing them and knowing how they vary on the periodic table itself. So labeling it on a periodic table definitely helps you to visualize it and see how those trends change on a periodic table directly. Okay, so let's start talking about those periodic trends. So the chemical and physical properties of elements depend on the electrons that they have, which is what we talked about in our previous lesson. How the periodic table was set up based off of the atomic number and the electron configurations that the elements had, and how we saw that law of octaves or 8, where there were just similar properties in specific elements that varied by 8 electrons. So while we discuss these trends, it's helpful to think of the atom with its electrons in shells orbiting the nucleus, which is how we have been thinking about the atom so far. So we've shown this many times where we have our nucleus here in the middle, and then we have these shells that go around it. It's going to be very useful to think of the electrons this way. So remember, our electrons are then just our little dots here and here all throughout those shells. Okay. And we have to remember that n is the shell number that the electrons are housed in. So with each new n, there is a new shell. So this would be n equals 1, that's closest to our nucleus. N equals 2, which is 1 further away. N equals 3, and so on and so on. It goes further and further as you go further out and have more electrons. So I'm just going to copy this in case we need it again in one of our slides. Okay. So the first thing we want to talk about is the radius of each atom. So the atomic radius increases from top to bottom down a group. So let's look at one of our groups here in our image. So here's group 1. So I'm going to start with group 1. And we see that the radius of these atoms, okay, increases as we go down the group. So we see that increasing ionic radius goes down a column, okay, and that's because with each new shell, so here we go from n equals 1 to now n equals 2 as being our outer shell, and then 3, and then 4, and so on, it's just becoming larger and larger and larger. Okay, so we have to accommodate more electrons. Even though they all have the same number of valence electrons, overall they just have more electrons in their core. So because we're increasing our number of core electrons, that means we're just increasing the size of the atom itself. Okay, so our atomic radius is going to increase down a group. Our next trend with atomic radius concerns how we go from left to right across a period. So within a period, here's period 2, okay, the atomic radius decreases from left to right. So as I add on one more electron with each one, the nucleus is pulling those electrons closer to the nucleus itself, causing the radius to decrease. Now it's not a large difference, okay, because once you start to get into that outermost shell, all of the valence electrons are in the same shell. It's not as large of a difference, so we see that those atomic radii, especially for like nitrogen, oxygen, and fluorine, are very close to each other. So it's not a large trend or a large change in the trend like we see when we go down a group. okay? But once what's happening is as you're increasing the number of valence electrons, those are being pulled closer to our nucleus. Our next trend is ionization energy, or IE, and that is the minimum amount of energy required to remove an electron from an ion or from an atom in the gas phase. So ionization, we see the word ion in that, so this is literally creating an ion. Okay, ionization energy is the amount of energy needed to remove one electron. So I'm going to change this "and" to one electron, okay, from an atom in the gas phase. So the result is an ion, a chemical species that has a charge. We've talked about ions multiple times throughout our previous lessons, in our previous chapters. So here we have sodium. In its natural or in its gaseous state, it does not have a charge, meaning it has the same number of electrons and protons. And then as it ionizes, okay, we pull off one electron. So here's one electron that we've pulled off. It has 1 minus charge because it's just one electron, meaning our sodium now has a +1 charge. So we've created the sodium ion. And we're left with one electron. We can quantify our ionization energies, and those have units of kilojoules per mole. Okay, remember from our previous chapter that joules is a unit of energy, and we typically see it in kilojoules rather than in just joules because it's a lot of energy. So the amount of energy that it takes to pull off one electron is 495.8 kilojoules per mole. Now this is the first ionization energy of sodium. So it's, there's a space here that should say IE sub 1 is equal to 495.8 kilojoules per mole. Because that's the first ionization, that's the first electron that we can pull off. We can pull off more electrons after that, okay? That corresponds to then the second ionization energy and the third ionization energy and so on, okay? But when we're talking about the first ionization, it's talking about the most loosely attached electron. If you remember from sodium, sodium is in group 1, so it has 1 valence electron. So it's very easy to pull off that 1 valence electron. After we take off that 1 valence electron, all those electrons now are core electrons, and it's like a noble gas. Remember, when we're talking about noble gas core, we have core electrons. Okay, those are a lot harder to pull off because they're all paired up, they're nice and close to the nucleus, and they don't want to be removed. So with each subsequent ionization energy, we're going to see that it takes more and more energy to pull off more electrons. Okay, so what is the trend across the periodic table? Well, the first ionization energy is going to increase from left to right across a period. So we see an increase in that ionization energy from here to there, from left to right. So we have lithium, that's at 520. So again, that's in group 1. So it has 1 valence electron. It's sitting in an s orbital by itself, right? So this is lithium, this is 1s2, 2s1. If we show that orbital diagram, it just has 1 electron in a box right there, and it's a lot easier to pull off that electron. If we go to beryllium, that's much higher. Okay, so that was lithium. If we look at beryllium, that's 1s2, 2s2. Now I have 2 electrons. Now they're paired up, and remember, electrons would rather be paired. Okay, so they're paired up. It's a lot harder to take off that one of those electrons now that they're paired up and spinning oppositely. And then as we go further and further down, it's the same concept as we get now into our p orbitals. Okay, if we have 1 electron, it's a lot easier to pull off that 1 electron. But as I create more and more electrons that are paired up, so here's fluorine, okay, it's a lot harder to pull off those individual electrons. Then if I go to neon, we're talking about a full p orbital, full p shell, so all of those electrons are paired up, so its ionization energy is really high. So once we get to the end of a period, all of the electrons in that shell are paired up and they don't want to be removed. Okay, so it takes a lot more energy for those electrons to be removed. So when you're thinking about ionization energy, it's very useful to draw out the electron configuration and the orbital diagram and look at what electron is being removed and would it take more or less energy to remove that electron. Would it be more favorable to remove an electron because it's only one by itself in an orbital? Would it be a lot harder because more of them are paired up? Those are the things you have to think about with ionization energy. Now there are a few exceptions based on where some of these electrons are, which I believe is on my next slide, but I'll talk about it here. So if we look at beryllium and boron, I'm going to pull these over here. So we said beryllium is 1s2, 2s2, so its valence shell has those two electrons. So that's beryllium. If we do boron, we have 1s2, 2s2, 2p1. So its valence shell is now a 2s and a 2p. Okay, so, but there's only one electron in that 2p. Okay, so this one electron here is a lot easier to remove. So this electron is a lot easier to remove compared to, say, this electron here. Okay, because these electrons are paired and in a filled shell, whereas this electron is unpaired and in an unfilled shell. So boron, it would be more energetically favorable to remove this electron so that you're just left with those two electrons paired up in the 2s orbital. So if you look at what the ionization energies are, beryllium and boron, boron's is a little bit lower because of that one unpaired p electron. So it's a lot easier to pull off that p. And we see that trend throughout here. Right, each of these, they're generally either really close to each other or one's higher or one's lower. Okay, now a similar thing happens in nitrogen and oxygen for the same purpose, except now we have nitrogen, which has 2s2, 2p3, whereas oxygen has 2s2, 2p4. Okay, they change by one electron. Here, nitrogen has a half-filled p orbital, or half-filled p shell. Okay, and that makes nitrogen very happy. Whereas in oxygen now we have one of these electrons that could easily come out and be left with a half-filled shell. So this electron is a lot easier to remove because it's paired up and the p orbitals would rather be half-filled or whole-filled. So that's what we talked about in our previous lesson with those exceptions to our rules of electron configurations. Our shells would rather be half-filled or whole-filled. And while that moving of electron only happens in the s and the d orbital, which is what we talked about with our electron configurations previously, this is a case where electrons just prefer or are more energetically favorable in a half-filled or whole-filled shell, so that does change their ionization energy or the amount of energy that it takes to remove one of those electrons. Okay, so that's why we see this trend in nitrogen and oxygen where the ionization energy of oxygen is a lot lower than nitrogen because nitrogen has a half-filled p orbital, whereas oxygen has this extra electron compared to nitrogen that is easier to remove. Okay, so we see that also with phosphorus and sulfur, and then as we go down the periodic table, it gets closer together where those ionization energies are almost the same. Okay, so this trend is shown here, and this is an image from your textbook. So electrons that are paired are harder to remove than unpaired electrons, so the ionization energy changes. So we see that this is what we were talking about before, that electrons or elements and electrons in group 2A are harder to remove, whereas compared to 3A, where we have that one unpaired p electron, that's what we were just talking about with beryllium and boron. Okay, so let's see, where do we see that? Lithium, here's beryllium, and then there's boron. Beryllium and boron. Okay, then our next one is nitrogen and oxygen. We also see that change, and you see it a lot through this trend. So we're going up and then we go down, then we go up, 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 then we go down. And those down portions are again in that, period, what is that? 5 to 6, or yeah, groups 5 and 6, and then also groups 2 and 3. Okay, so this is just prevalent in groups 2 to 3 and groups 5 to 6. Okay, so this is again just the other oxygen nitrogen example. So the electrons that lie in a half-filled shell with spins maximized, so that's our Hund's rule. We want to maximize our spin. They are harder to remove. Okay, so here's nitrogen and here's oxygen, which again happens right there. So we see that change in ionization energy. So ionization energy does tend to increase as you go across the period, but there are exceptions due to where the electrons are and if they would prefer to be removed or not. Okay, so you have to keep that in mind. Okay, now the opposite of ionization energy is the trend of electron affinity. And electron affinity is the negative of the energy released when an atom in the gas phase accepts an electron. So we're now bringing in an electron instead of taking the electron out. So instead of removing the electron, we're adding the electron in. Okay, so it's essentially how much does the atom want an electron. And this is where we have to remember our rule of 8. We would rather have, 8 electrons. 8 is great. We're going to talk about that a lot throughout this chapter and our next few chapters, why 8 is great. And it's because 8 is noble gas. Group 8 is noble gas. And those are our most stable elements. Okay, so as we get closer to our noble gases, that electron affinity is going to become a lot higher because we want to take on electrons to get to 8 electrons total. So, like ionization energy, electron affinity increases from left to right across a period because it's easier to add an electron as the positive charge of the nucleus increases. Okay, so as we add more protons, that increases our positive charge, meaning it's easier to take on an electron. So, we have fluorine, chlorine, bromine, iodine. They would love to take on one electron. So let's look at the orbital diagrams as to why. So let's look at fluorine. That's 1s2, 2s2, 2p5. Okay, so its orbital diagram is 1s2, 2s2, 2p5. Okay, so fluorine, chlorine, bromine, iodine, they all have this, S2p5 thing where they're missing one electron. They have 7 valence electrons and they want to get to 8. So they only need 1 electron to get to a full shell in the p orbital. So it's a lot easier to say, okay, I'm going to take on an electron and add it there. So they really want that extra electron to get a whole filled shell. Because remember, half filled and whole filled make our atoms happy. Okay, so we also have cases like, let's see, carbon, silicon, germanium, and tin. These are again similar to our exceptions before. So let's look at carbon. It has 1s2, 2s2, 2p2. Okay, so we have 1s2, 2s2, 2p2, and if we look at that, it's 1 electron away from being a half-filled shell. So its electron affinity is a lot higher in comparison to its surrounding elements, so boron and nitrogen. Okay, so this is boron, that's nitrogen, because it's 1 electron away from a half-filled shell, which again makes us happy. We like a half-filled shell and we like a whole-filled shell. So electron affinity does increase across a period, but there are exceptions to those rules because of how the electrons would be added and make a more energetically favorable orbital. So again, just like ionization energy, you may find it easier to draw out the orbital diagram and think what electron needs to be added, where would it be added to, would that give me a half-filled shell or a whole-filled shell, what would happen there, okay? So just think about where the electrons need to go for both ionization energy and electron affinity, but they have the same trend for the same but opposite reasons. Okay, so this is what we just talked about, the notable exceptions. So here's another example going into group 1 and 2. So this is, let's call it lithium and beryllium. So lithium has a higher electron affinity compared to beryllium because it has 1 electron that's unpaired. So it's a lot easier to add on an electron here and make a whole-filled s orbital. Whereas with beryllium, okay, and anything in group 2 really, it has a whole-filled s shell, okay, and if I wanted to add an electron, I would have to go into a p orbital, which is not as energetically favorable because it's higher in energy. So I wouldn't want to put that electron there. So my electron affinity is very low because I don't want the electron. Okay, so just think about where the electrons would be going and if that would be energetically favorable. Specifically, we want to maximize spin, half-filled, and whole-filled shells. Okay, and then this was the example I had with carbon. Okay, we added an electron compared to nitrogen. It's a similar thing there as well. So it happens for groups, let's see, groups 1 and 2, and groups 14 to 15, or 4A, 5A. So they're notable exceptions. They're particularly more prevalent higher in the periodic table. As you go lower down, like we saw with ionization energy, they don't change as much, but you do just have to think about where the electrons are going to be going. Is it easier or harder to add those electrons in order to maximize our spin and our whole and half-filled shells? Okay, so next up is the trend of metallic character. So metals tend to be shiny, lustrous, malleable, and ductile. Okay, so this is like, if you think of aluminum foil, that's aluminum, that's a metal. Okay, it's very easy to use aluminum foil, crunch it up, put it over your food before you put it in the fridge or whatever. Okay, so it's very shiny, it's very malleable. Okay, metals are also good conductors of heat and electricity. It's why we use them in wires in our homes and in our cords and everything like that. And they also have low ionization energies. Okay, they would rather form cations rather than anions. So it's really easy to remove those electrons. So we have to remember that our metals make up a majority of our periodic table, and in this periodic table, and as we've labeled them before, is everything that's labeled in green. So this whole kind of left side, center, and everything like that on our periodic table, these are all of our metals. So we have a lot of metals. So they all tend to be shiny, lustrous, malleable, ductile, conductors, and have low ionization energies in order to form their cations. So they would rather give up their electrons in order to form that cation. So they will happily give up those electrons, so their ionization energy is a lot lower. Next up, we have the character of nonmetals. So our nonmetals is everything in blue, which is not a lot of elements on our periodic table, but they do a lot of things. If you take organic chemistry, you'll see a lot of stuff with just carbon, nitrogen, and oxygen. That makes up an entire class right there. So even though there's not a lot of nonmetals, we do a lot with them. And nonmetals tend to vary in color. They're usually not very shiny. Okay, think of carbon. That's a good one to kind of think about. That's a classic nonmetal. This is like the lead in our pencils and stuff like that. Charcoal is a form of carbon. It's not very shiny. It's kind of dull and, brittle. They're not malleable in any way. If you think of like charcoal on a grill, it's very easy to crush those charcoals. They're also poor conductors of heat and electricity. Obviously, there's some exceptions to that, like carbon. And they also have very high electron affinities. So they want to form anions, so they want to take on electrons. Okay. Finally, we have the metalloids, which is everything in our little stair-step region here, everything labeled in orange. Those are our metalloids. And these are really intermediate. Their characters are kind of intermediate between both nonmetals and metals, so it kind of varies depending on what element you're talking about. And that concludes our section on periodic trends. Again, this section was mainly definitions and something we have to label our periodic tables with. The big kind of ideas that come out of this is thinking about where the electrons are going. So we started with atomic radius that changes with more electrons, how differing in our number of shells in our atom will change our atomic radius, and then the amount of energy that it takes to either remove an electron or add an electron to an element to either be more or less energetically favorable. Okay, so next up, we're going to talk about electron configurations of ions. Now, we've talked about ions in previous chapters, but just to review, we said that cations are positive. Remember, that's how we think of it. Cat is in the word cation. Okay, it's positive. You can also think of it as it has a T, which is a plus sign, so it's positive. Okay, so they have a positive charge, which means they have more protons than electrons. So electrons were lost or removed. Okay, so certain elements prefer to lose electrons and become cations. This would specifically be all of our metals, most of our metals, so groups 1 and 2, and our transition metals. So we have to remember that. And if it's a metal, it's going to create a cation. They would rather lose their electrons, so they have a low ionization energy. They will happily remove electrons in order to form cations. Next, we have anions, which is a negative ion. So this is where we have more electrons than protons. So electrons were added. Okay, and again, certain elements would prefer to gain electrons and become anions, and this is more typically our nonmetals. So that would be our nonmetals in groups 5A, 6A, and 7A. I'm just saying my A notation there. So groups 5A, 6A, 7A, or 15, 16, and 17. They prefer to form anions, so they have a really high electron affinity. They'd want to take on those electrons. Okay, so let's do some review. Let's remember how to count up all of our protons and electrons when we're given an element and its charge. So our first example here is calcium 2+. So the 2+ means that I have 2 more protons than electrons. Okay, so we have to remember that when we're determining our charge, it equals the number of protons minus the number of electrons, and whatever sign comes out tells us if it's a positive or negative charge. Okay, now the number of protons is never going to change. When we're forming ions, we're only varying our number of electrons, because if we change our number of protons, we change our element. So in order to find how many protons calcium has, well, we just have to look at the periodic table. So pull out your periodic table, look for calcium, see where it is on the periodic table, and that will tell you the number of protons. Calcium is element number 20, meaning it has 20 protons. And if calcium 2+ has 2 more protons than electrons, that means our number of electrons is 18. We can plug that in. We have 2+ is equal to 20 minus our number of electrons. Subtract off 20 from 2, and we get electrons is equal to 18. Okay, so our number of electrons is 18. That leaves us with a 2+ charge. Our next example is oxygen 2-, which means we have 2 more electrons than protons. So oxygen 2-, let's find it on our periodic tables so we can find our number of protons. Oxygen is element number 8, so it has 8 protons. And if the 2- charge means I have 2 more electrons than protons, that means I have 10 electrons. And if we do our math, we can do 8 minus 10 is equal to -2, which is our charge. Okay, so always double check your charges, making sure that you've noted how much protons and electrons each of those ions has. Okay. For these next 3 problems or 3 examples, what I want you to do is pause the video, go through these 3 elements, ions that I have, determine their number of protons, find them on the periodic table, and then using what we just did with our first 2 problems, determine how many electrons they have. Let's start off with nickel. Nickel 2+. So we have nickel on our periodic table is element number 28. So it has 28 protons. If it has a 2+ charge, that means it has 2 more protons than electrons. So that would mean our number of electrons is 26. Next up, we have selenium, Se, selenium 2-. If we find selenium on our periodic table, it is element number 34, so it has 34 electrons, or protons. And if we have a 2- charge on that selenium, that means we have 2 more electrons than protons, so we would have 36 electrons in our selenium ion. Finally, we have iron, iron 3+. If we find iron on our periodic table, we would find that it is element number 26, so it has 26 protons. And with a 3+ charge, that means I have 3 more protons than electrons, so I'm going to subtract that 3 from my protons and get 23 electrons. Okay, so now that we've reviewed how electrons are being added or removed to determine our ions, let's apply that to our electron configurations, because as we learned in our previous lesson, electron configurations tell us where those electrons are, how they're organized in the atom. So if I'm removing those electrons, I'm not just removing them from any orbital, I'm removing them from specific orbitals. So to write the electron configuration of an ion formed by a main group element, we first want to write the configuration for the atom, and I'm going to add a note there that it should be the neutral atom. So as you find it on the periodic table. Then you're going to take that configuration and either add or remove the appropriate number of electrons from the outermost shell. So that's going to be our highest N, or you can think of it as our valence shell. We're either adding or removing electrons from our valence shell. Okay, so let's look at sodium. Sodium is in group 1, and it prefers to create an ion with a 1+ charge because it has one valence electron. So our valence electron in sodium is the 3s1. The 3s1, okay? So if we're creating a sodium 1+, that means I'm removing an electron. So that one electron that's going to be removed is coming from the valence shell, or the highest N value. So it would be the 3s1. So our sodium ion is then 1s2, 2s2, 2p6. That shows us that we have now 10 electrons. In sodium there are 11 protons. So in total, I have a 1+ charge, which corresponds to my 1+ charge of sodium there. So we've removed an electron to create a cation. Okay, let's look at an anion. Let's look at chlorine. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5, and we're creating a chlorine 1- ion, so we've added one electron to form an anion. Okay, so it's a negative ion. We have a negative charge on there. So that one electron is going to be added to our outermost shell, and specifically to our p orbitals, because if we look at it, change colors, if we look at our 3s and 3p, I have 3s2, 3p5, 1, 2, 3, 4, 5. The one electron that we're going to add only has one place to go, and it's going to go right in that p orbital. And that's so that we can have that filled p orbital shell, because a hole filled shell makes our elements happy. Okay, so our ion configuration now has that 3p6 there. So we have a total of, 18 electrons. Chlorine has 17 protons, so if we subtract those, we get a 1- charge, which relates to our 1- charge on chlorine. Okay, so when we're writing out electron configurations of an ion, we first want to write the configuration of the neutral atom, and then determine where the electrons are either going to be added or removed from. Specifically, they're going to be added or removed from the highest N value or the valence shell, wherever you think of those are the same thing. So wherever you think of, however you think of that. Okay, so it's coming from the highest N or the valence shell. Okay, so species with identical electron configurations to the noble gas, to the right of them, are considered isoelectronic. So if we look at sodium, which when we had Na+, we had 1s2, 2s2, 2p6. That has 10 electrons. Now let's look at our periodic table. What other element also has 10 electrons? Well, neon does. Neon has 10 electrons, and it has an electron configuration of 1s2, 2s2, 2p6. So, because these have the same electron configuration, they are considered isoelectronic. They have the same number of electrons in the same electron configuration, because electrons are just, numbers that we add in. So if they have the same number of electrons, they have the same electron configuration. So they are isoelectronic. Now, if we look at these monoatomic ions, so here's, carbon 4 minus, nitrogen 3 minus, oxygen 2 minus, fluorine 1 minus. These all have the same electron configuration as neon, because if I have carbon 4 minus, that means I've added 4 electrons, so I have 1s2, 2s2, 2p6 now, because I've added 4 extra electrons to my p orbital of carbon. The same goes for nitrogen, as well as oxygen and fluorine. They all have the same electron configuration of neon. The same goes for phosphorus, sulfur, and chlorine. They all have the same electron configuration of argon when these are in their ionic form. And the same goes for the cations. You just have to work backwards. Okay, so isoelectronic means that they have the same number of electrons, whether they're in an ion or in their neutral form. So let's practice some of these. Let's write the electron configurations for the following ions and then determine which other element they are isoelectronic with. So we have nitrogen 3 minus. So our first step is to write the electron configuration of nitrogen. You may find it useful to pull out your diagram for writing electron configurations, the one with the arrows. I don't have it here because by starting this lesson, you should have already mastered writing regular electron configurations and completing your ALEKS homework. So I am under the assumption that you have a good grip on that, but if you do not, that's totally fine. We are still learning, so feel free to pull out that diagram and utilize that as we go through these problems. So let's look at nitrogen 3 minus. So we're going to first draw out our electron configuration of nitrogen, which is 1s2, 2s2, 2p3. And what we're going to do, so this is our neutral nitrogen. We're going to now add our 3 minus charge, meaning we are adding 3 electrons. So those 3 electrons are going to be added to our highest n value and to our orbital that still has space, which is going to be our p orbital. So our electron configuration becomes 1s2, 2s2, 2p6. Okay, so because we added those 3 electrons, they went into the p, and now we have a 2p6 there. That means we have a total of 10 electrons. So what other element on our periodic table also has 10 electrons? Well, that was neon. So it is isoelectronic with neon. Let's try barium 2+ next. So barium is element 56, so it may be easier to draw this as the electron configuration as a noble gas core, so we don't have to draw all of them out because we know those core electrons are not going to be removed. So our noble gas core for barium is xenon 6s2. Now the 2+ tells us that we are removing 2 electrons. So those 2 electrons are coming from that 6s shell. So we're left with just xenon. But we can't write an electron configuration as just a noble gas. We have to show where all of the electrons are. So we can write this instead as if we were writing this for xenon, which would be krypton 5s2, 4d10, 5p6. Okay, so that has a total of 54 electrons. So this is still isoelectronic with xenon. So it has the same number of electrons as xenon. And again, I just went from xenon to a krypton noble gas core just so I could show the electron configuration and where those electrons are, because writing it as just a noble gas is not an electron configuration. Let's try this again with beryllium. Feel free to pause the video and try this one on your own, and try the next one as well on your own, just to see if you're getting a handle on it, and then check your work with what I'm doing. Beryllium is element number 4, so we only have 4 electrons. So we have 1s2, 2s2. If it's a 2 plus, we are removing 2 electrons because we're going to have more protons than electrons, so electrons need to be removed. So that leaves us with 1s2. Those electrons that are being removed are coming from the 2s orbital, and those are the 2 electrons that we are removing in total. So we're left with a electron configuration for Be2 plus as 1s2. So that has a total of 2 electrons. What other element on our periodic table also has 2 electrons? Well, that would be helium, or He. Oops. He. And if you'll notice, our isoelectronics are always going to be noble gases. Because when we're creating ions, we always want to move towards a noble gas core, because noble gases are the most stable. Okay, our last example is bromine, 1 minus. I'm going to write bromine as argon 4s2, 3d10, 4p5. Okay, just so I don't have to write out all of the electron configuration, but if you want to write out the full electron configuration, you're more than welcome to do that. If you're still practicing how to do the noble gas core, that's totally fine. Feel free to pause your video, write out the full electron configuration, find the noble gas core, and just double check that your starting electron configuration is the same as mine. And if we're doing Br minus, that means we're adding an electron, because the minus tells us that we have more electrons than protons, so we have to add electrons on. So this then becomes argon 4s2, 3d10, 4p6. So we added that extra electron to the 4p5 because that p orbitals there have 1 unpaired electron, so that extra electron went in and filled that space to have a full-filled p orbital, which makes us happy. And this now has a total of 36 electrons, which is isoelectronic with krypton. Again, another one of our noble gases. Now, I want to make a very important comment about the d block ion configurations, because this is where I typically see students get confused or get these specific electron configurations wrong. Okay, so the ions of d block elements are formed by removing electrons first from the shell of the highest n value. Okay, so the comment that I want to make is we have to remember that valence electrons in d block elements, which is our transition metals, so those center metals on our periodic table, the valence electrons in d block come from the s and the d. And if you remember from our previous lesson, that's where we start to have the changes in our n value. So we went from 4s to 3d or 5s to 4d because they're close in energy. Okay, so they switch on us. So we have to remember that when we are forming ions for d block elements, we remove electrons from the highest n value first. So that would be the 4s, the 5s, the 6s. It's always going to come from the s first because those s orbitals have the higher n value. So take from s first, because those have the highest n value. So let's look at the example of iron. Iron is able to form an iron 2+ ion. So it loses 2 electrons, and those electrons are lost from the 4s subshell, not the 3d, because 4s has a higher n value. So if we look at, here's iron neutral, argon 4s2, 3d6. when I remove my 2 electrons, those electrons are going to be removed from the 4s first because this is the highest N value. 4 is higher than 3. So our electron configuration for iron 2+ then becomes argon 3d6. Okay, so because 3 is lower in N, okay, then the electrons aren't taken from there. Another way to think about this is if we think about our atom here, okay, I'm going to add another layer to this image. Here's N equals 4. So in iron, I have 2 electrons in the N equals 4. Okay, that's our 4s2 electrons there. Okay, that corresponds to here. Our 3d6 corresponds to this layer in here. Okay, the only way that I'm able to remove electrons is from the outermost layer first. It's like an onion. You gotta peel off the top layers first before you get into the middle. Okay, so if I want to remove those electrons, I first have to remove the electrons from the 4 before I can even get to the 3. Okay, so this is where thinking of the atom as these layers with shells surrounding it is easier to think of than what we're seeing in our ordering of our electron configurations. So you just have to remember highest N first, and then we go from there. Because these are shells, we have a shell that has the electrons in it. So the highest N is our outermost shell. So we have to take from that shell first. Okay. Now, iron can also form a 3+. Iron can also form a 3+ ion. So, if we look at iron by itself, it's neutral. It's argon 4s2 3d6. If I'm removing now 3 electrons, 2 of the electrons are coming from the 4s, and then that's going away. And then that 1 extra electron is now coming from the d. So now that I've removed that outermost N, okay, so here's my 4, I'm going to draw it in a quarter way over there. Now that I've removed the electrons from the 4, I can now access the 3 to start taking away electrons from. Okay, so once you get rid of the electrons from the highest N, then you go to the next highest N, which would then be 3. So our final electron configuration for iron is then argon 3d5. So this still shows that we have 23 electrons, but iron has 26 electrons, so we have a 3+ charge. Okay, so always take from the highest N, and if you have to then change from one N to another, that's totally fine as long as you're going in order, because you have to think of these as shells. Like an onion, you have to peel away the top of the onion before you get to the next layer. Okay, so think of it like that. So let's practice a few of these for our D block elements. So we have zinc 2+. So zinc has a electron configuration of argon 4s2 3d10. And if I want to remove 2 electrons to create a 2+ charge, those 2 electrons are going to come from the 4s. Okay, I'm removing from the 4s. So I'm going to be left with argon 3d10, because I just essentially got rid of that entire s orbital. I got rid of the 4 shell in general. It's not even there anymore, so it just goes away. We just get rid of it. Next up we have manganese, Mn 2+. So manganese is argon 4s2 3d5, and again we're removing 2 electrons. Those 2 electrons are going to come from the 4s, so I'm really just getting rid of the 4s, and I'm left with the 3d. Now if I wanted to make it manganese 3 plus, I would then subtract off another electron. That electron would come from here, so I would be left with argon 3d4. Okay, so let's try our last example. This is chromium 3 plus, and chromium is one of our exceptions, one of our electron configuration exceptions. So take a second and see if you can remember how to write the electron configuration for chromium based on what we've talked about for exceptions in our previous lessons. For chromium, our electron configuration in our neutral form is chromium 4s1 3d5. This is where we've moved an electron from the 4s up to the d. Oops, that's not enough. So that we have 2 half-filled orbitals. Okay. Now our rule still applies when we're creating an ion for this. So we're still going to remove 3 electrons, and our first electron is going to come from, first come from our highest end, so we're going to remove that 4s, but that only removed 1 electron, so our next 2 electrons are going to come from the 3d. So we are going to be left with argon 3d3, because we've essentially taken these, we've removed those electrons. We've gotten rid of that 4s, and we've changed that 5 now to a 3. So we only have 3 electrons left in our d orbital, so it becomes argon 3d3. Okay. Let's do some more practice. Before I jump in and we work through these together, what I want you to do is pause the video and write out the electron configurations for each of these elements, and then try to determine their electron configurations for their ions. So first start with your neutral element, and then determine where the electrons either need to be removed from or added to. Okay, our first element is Nb, or niobium, element number 41. Because there's 41 electrons, you might have found it easier to write out the noble gas core configuration, which again is fine, because the electrons that are being removed are coming from the valence shell, so those core electrons are not being removed or added to or anything. So niobium, we start with krypton, 5s2, 4d3, okay, for a total of 41 electrons. If we have niobium 2 plus, that means we're removing 2 electrons. And this is a transition element, so those 2 electrons are going to come from the highest end first. Okay, not our last place that we put electrons, it's our highest end first, because we have our layers that we need to remove first. Looks like a Wi-Fi signal. Okay, so we've removed our 2 electrons from the 5s, so our ion then becomes krypton 4d3. Next up we have selenium 2 minus, and we have argon 4s2 3d10 4p4. Okay, and we're adding 2 electrons in order to get a 2 minus charge. So because this 4p has 4 electrons. 2 of those are unpaired. Those 2 electrons are going to be added to our 4p. So we're left with argon 4s2, 3d10, 4p6. Okay, and what we don't want to do is just write it as krypton. We don't want to do that. We can't do that. An electron configuration can't just be an element. It can't just be a noble gas. So it would be argon 4s2, 3d10, 4p6 to show that those 2 electrons went into the p orbital. Again, they're being added to the highest n state, or highest n orbital. Okay, next up we have strontium, Sr, strontium 2+. Sr strontium is, its electron configuration in its neutral form is krypton 5s2. And if we're having a 2+ charge, that means we're removing 2 electrons. So that then just becomes krypton because we removed these 2 electrons. But I can't just write the noble gas as its electron configuration, so we need to go back one. We need to go argon 4s2, 3d10, 4p6, which is the same as what we have here, meaning that the Se, selenium 2-, and the strontium 2+ are isoelectronic with krypton. Okay, they have the same number of electrons, the same electron configuration, meaning they are isoelectronic, and they are isoelectronic with each other as well as with krypton. Okay, finally we have potassium, K. K is potassium, element number 19, and its electron configuration is argon 4s1. And it has a 1+ charge. If it has a 1+ charge, that means we're subtracting off 1 electron so that we have more protons than electrons to leave us with a positive charge. So if we remove that 1 electron, it's coming from our 4s. So we've created argon, which equals neon 3s2, 3p6. Okay. So, how does this affect the radius when we're creating ions, when we're adding and removing electrons? How does this affect the radius of our atom? Well, we talked about atomic radius before, and we said it depends on the number of layers, the number of shells that we have, n values. As we increase the n value, we increase the atomic radius. But now that we're changing those number of electrons, and for some of these removing entire shells, how does that affect the radius? Well, the ionic radius is the radius of a cation or an anion. When an atom loses an electron to become a cation, so if we're creating a cation, so we're looking specifically at this portion of our periodic table in our image here, so all of our metals, group 1 and 2, as well as some in 3A, when we're forming a cation, the radius decreases because we're taking away one of those shells, one of those orbits. Okay, so here I have sodium. Here it is in its neutral form, so it has all of its electrons. When I remove its electron, its 1 electron, and create its ion, you're essentially just getting rid of that entire shell. You're removing it, so its radius decreases. Okay, so when we create cations, the radius is going to decrease due to a reduction in our electron-electron repulsions. And there we see that significant decrease when all of the valence electrons are removed and we're left with just the core, which is what this image was showing. Okay, so in our image up here, we see one side, this is our neutral side, and then this is our ion side. As we go from neutral to ion, that radii significantly changes because we're just removing an entire orbit of that element. Now the trend in the radius still is that lithium's radius is still going to be smaller than sodium's and potassium's because they just have more layers. They have more core layers themselves, or core shells, which is fine. But we have to think about how the ionic radius is going to change as I remove the electrons. Now, when an atom gains one or more electrons and becomes an anion, so we're making an anion, so we're looking at our non-metals over here, groups 15, 16, and 17, or 5A, 6A, and 7A. The radius is going to increase because we're increasing our electron-electron repulsions. We're putting electrons into that outermost shell, and they're repelling each other more because they don't like each other, okay? So we see here, again, we have our neutral side and our ionic side. The neutral side, the neutral radius, is smaller than the ionic radius. So it's the opposite of what we were just seeing with the cation. As we add more electrons, our radius is going to increase. Now, the trend, again, is still the same as we go down, that the ionic radius is going to increase as we go down a period, just because of those core electrons. There's just more core shells in those elements. But again, what we're focusing on is how the radius changes as we go from neutral to ion, and where those electrons are going and how many we're adding. So that's the end of our lesson, and overall our end of lessons in Chapter 4. Chapter 4 had a lot of focus on periodic trends and mainly electron configurations. Where are we housing those electrons? How do those electrons affect the trends in our periodic table? Okay, so this chapter was all about electrons. Before you move on to your next chapter, please make sure that you are completing your ALEKS homework and your test for this chapter, and make sure that you are mastering these electron configurations, where those valence electrons are, understanding how to remove and add electrons to create ions, because we will be utilizing that in our future chapters to build on this topic in order to create molecules.